Hey everyone, welcome back for another deep dive. Today we're going to be looking at something that's
Mhm.
pretty crucial to the future of, well, pretty much everything.
Yeah.
We're diving into large language
Dun-dun.
models, LLMs, yeah, those AI systems that can, write like Shakespeare and answer your questions like a walking encyclopedia and
Right.
even generate code.
Mhm.
But all that brain power,
It comes at a cost.
it does come at a cost.
Yeah.
And I mean, a real cost
A
computationally.
big one.
Yeah, think massive energy use,
Yeah.
expensive hardware,
Uh-huh.
and those sometimes frustratingly slow response times.
Absolutely. And that's one of the biggest challenges right now in AI research,
Hmm?
figuring out how to make these LLMs more efficient.
Yeah,
How to get them to think smarter, not harder,
I
like
like
so
that.
to speak.
Yeah, because it's not just about saving money or energy.
Right.
It's about making this amazing technology accessible to
Mhm.
everyone, not just these giant tech companies.
Exactly. And that's what makes this research paper we're looking at today
Hmm.
by Daman Arora and Andrea Zanette from Carnegie Mellon University. So
Wow.
exciting. They've come up with a new way to train LLMs to reason more efficiently,
Hmm.
especially when it comes to solving problems.
Okay.
It's like they've given these AI systems a
Yeah,
crash course in strategic
I
thinking.
love it. So let's break this down a bit.
Okay.
The paper talks about these chain of thoughts or
Oh,
cutsies.
yeah.
What are those and why are they so important for this research?
So imagine you're trying to solve a logic puzzle.
Okay.
You might jot down some notes, draw diagrams,
Yeah.
or even talk yourself through the steps.
Hmm.
That's kind of what a chain of thoughts is for an LLM. It's like the LLM is writing down its thought process
Okay.
step by step before giving you the final answer.
Interesting.
These intermediate steps are represented by tokens,
Tokens.
which are basically units of information the LLM processes.
So the more steps the LLM
All
takes,
right.
the longer its chain of thoughts,
Yes.
the more tokens it uses,
Uh-huh.
and the more computational power it needs.
You got it.
That's where things can get a little inefficient, huh?
Yeah, and traditional LLMs, especially those trained for complex reasoning,
Hmm?
tend to generate really long cots,
Okay.
even for relatively simple
So
problems.
they're overthinking things,
It's like they're overthinking it, yeah, exploring every possible avenue,
and that gets expensive.
which can be computationally very expensive.
So Aurora and Sonnet are trying to streamline that thinking process, get the
Yes.
LLMs to focus on the most important steps,
Right.
kind of like creating mental
That's a
shortcuts.
great way to put it.
And they're using reinforcement learning or RL for this.
Exactly. RL is a powerful technique.
Okay.
You can think of it as training AI systems through trial and error.
So like teaching a dog a new trick.
Yeah, like rewarding them when they do it right.
Got you. So they're rewarding the LLM for being more efficient.
Yes.
But how do you actually do that? How do you teach AI to think strategically?
Well, that's where the real cleverness comes in.
Okay.
They modified what's called the objective function
The object
that
block rule.
guides the LLM's learning.
Okay.
Imagine you're training for a marathon.
All right. I'm training.
Your objective function might be to minimize your finishing time.
Sure, makes sense.
But what if you also added a penalty for every extra ounce of weight you're carrying?
Oh, that would definitely encourage me to streamline my gear.
Right.
Yeah, and maybe even shed a few pounds.
Exactly. In a similar way, Aurora and Zanette added a penalty to
Ah,
the LLM's objective function
ah.
that discourages it from generating overly long cots.
So like a little nudge.
Yeah, it's like giving it a nudge to be more concise.
So it's not about dumbing down the OAM or limiting its knowledge.
No, not at all.
It's about teaching it to use that knowledge better.
Exactly. It's about finding that sweet spot between accuracy and efficiency.
Like the sweet spot.
Yeah,
Okay, so they have this way of training LLMs to be more efficient.
right.
But how do they know it's actually working?
Oh, that's what we're going to talk about next.
All right, I can't wait.
Stay tuned.
All right, so they've got this clever way of training these
Yeah.
LLMs to be more efficient.
Hmm.
But how do they actually know if it's working? Did they test it out?
Oh, they absolutely did.
Yeah.
And this is where it gets really interesting.
Hmm.
They tested their approach on not one,
Okay.
not two, but three different data sets,
Oh, wow.
each with its own level of
A
difficulty.
three-level challenge for these LLMs. All
Eight.
right, so what were these data sets?
Well, first up was GSM-8K, a
GSM-8K.
data set of grade school math problems.
Okay, so like word problems.
Yeah, I think word problems.
The kind that might give me flashbacks to elementary school.
Exactly, but nothing too intense mathematically.
All right, level 1 relatable math problems.
Yeah.
What about level 2?
Level 2 cranked up the heat
Okay.
with math, a data set of high school level math problems.
Ooh, getting a little harder.
Definitely more challenging,
Yeah.
but still something that most people have encountered in school.
Okay, makes sense. And for the final boss level?
They went all out with AIM
AIM.
2024,
Okay.
a data set of competition level math problems.
Wow.
designed for top math students.
So like the best of the best.
Exactly. This is where they really wanted to see if their approach could hold up.
Right. So did these efficiency-trained LLMs pass the test?
The results were incredibly impressive.
Okay, good.
Across all three datasets,
Uh-huh.
they saw significant reductions in token usage.
Which, remember, is a measure of computational costs.
Exactly. And here's the best part. This efficiency boost didn't come at the expense of accuracy.
Oh, wow.
The LLMs were still able to solve the problems correctly.
So they were thinking smarter, not harder.
Exactly.
That's amazing. But wait, if it's all about finding a balance
Yeah,
between efficiency and accuracy,
right.
is there a way to control that balance?
That's another really cool thing about this research.
Okay.
They were able to control that trade-off
Uh-huh.
using a single parameter, which they called alpha.
Alpha. Okay.
So a higher alpha means the LLM focuses more on efficiency,
Okay.
potentially sacrificing a bit of accuracy.
So it's like a slider.
Yeah, it's like a slider almost.
You could adjust it depending on what you need.
Exactly. It gives developers a tool to fine-tune the LLM.
Really interesting. But was there anything that surprised them during the research?
Actually, there was.
Oh, really?
It came up during their ablation study.
Ablation study. Now, that sounds intense.
It's basically a way of removing or altering parts of their method
Okay.
to understand how each part impacts the result.
So like a scientific detective game,
Exactly.
trying to isolate the key ingredients.
Right, and they found something really counterintuitive.
Oh, this is what I like.
Remember how we talked about the reward function in RL?
Yeah, it gags the LLM's learning.
Right, well, there's another important piece called the advantage function.
Advantage function? Okay.
You can think of it like a compass.
Okay.
That helps the LLM figure out which actions are more likely to get a reward.
So the advantage function helps it navigate to the best solution.
Exactly.
What about it? What surprised them?
Well, in most RL research,
Uh,
you normalize the advantage function.
normalized meaning.
It means you adjust it to
Okay.
have a specific average and spread.
So like calibrating a compass,
Exactly.
making sure it's pointed in the right direction.
Right.
Okay. So what happened when they tried to normalize it here?
It actually made things worse.
Really?
Normalizing the advantage function actually led to a big drop in accuracy.
Wow.
It turned out that for this task, leaving it unnormalized worked much better.
So they had to break the rules a bit
Kind of, yeah.
to get these amazing results.
Sometimes you have to.
I love it. But why would unnormalized be better in this case?
That's a great question.
Yeah.
And it shows how important it is to really understand each problem. In this case, the researchers think normalizing might have flattened out some of the differences in rewards,
Oh, I see.
making it harder for the LLM to learn.
So it's like the LLM needed the full unfiltered signal to
Exactly.
learn effectively.
It just goes to show that in AI research,
Yeah.
there's still so much we don't know.
Right.
And sometimes the most oh, hey, our listener wants to join in. What's up?
Can we explain the object function with the main takeaway?
Of course. Let's break down the objective function.
Yeah, and think about what the LLM is taking away from it.
So remember that marathon example from earlier?
Yeah, the one where you're shedding pounds.
Right. The objective function was to minimize your finishing time.
And the takeaway there is clear, finish faster.
Exactly. The LLM is similar. It wants to maximize something
In this case, it's maximizing a combination of accuracy.
and minimizing the length of its chain of thought
The objective function guides the LLM to be accurate.
while also being computationally efficient.
So the takeaway is be right, but be brief.
Hopefully get a bit clearer.
And it sets us up for why they tested on simple problems.
Right. Like what is 1 + 1?
Exactly.
I think that's a great place to pick back up.
Agreed.
We've learned about these chain of thoughts,
Yeah.
how researchers are making LLMs more efficient,
Right.
and even this surprising finding about the advantage function.
It's fascinating stuff.
It really is. Welcome back to the show. We left off talking about some pretty groundbreaking findings in AI research.
Yeah.
This whole idea of training LLMs to be more efficient
Right.
without sacrificing their accuracy.
Mm-hmm.
It's pretty amazing.
It is.
And you mentioned that the researchers actually tested
Yeah.
their most efficient LLM
Uh-huh.
on a really simple question.
Right.
What is 1 + 1?
It seems simple.
It does seem super simple.
Yeah.
Why would they do that?
Well, it might seem overkill at first, but that's actually why it's so interesting.
Okay.
They wanted to see how this streamlined LLM trained for efficiency would approach a problem that's almost instinctual for us humans.
Like, it's so basic for us.
Exact.
We don't even think about it.
Right. It's a way of comparing how we think
Okay.
versus how AI processes information.
I see. So before we reveal the LLM's answer, let's think about how we would approach this.
All right.
If someone asked you, what is 1 + 1?
Yeah.
What goes through your mind?
Honestly, for most adults,
Uh-huh.
it wouldn't even be conscious thought.
It's instant.
It's instant, yeah, like a reflex,
Yeah.
just immediate recognition.
We just know it.
We know it. We see 1 + 1, our brains instantly go to 2.
No calculation needed.
Not really, no. It's pure pattern recognition.
Right. From years of ingrained knowledge.
Exactly.
It's like knowing the sky is blue.
Yeah, or that water is wet.
It just is.
But for an LLM, things are different.
Okay.
They learn by processing tons of data.
Right. Finding patterns.
So even a question like 1 + 1 could trigger a whole bunch of calculations and associations.
Because it's trying to find those patterns.
Right. It's like having access to a giant library, but not knowing which book has the answer you need.
I like that analogy.
So the researchers wanted to see if their training could help the LLM, cut through all that noise.
And find the most efficient solution.
Exactly.
Okay. I'm ready for the big review.
All right.
What did the LLM say? How did it answer 1 + 1?
So here's the LLM's response, and I'll read it in verbatim.
Okay.
Think to solve 1 + 1. I start by identifying the two numbers involved, which are both 1. Next, I add these two numbers together. Finally, the sum of 1 and 1 is 2. Think to solve 1 + 1. Follow these simple steps. 1. Identify the numbers to add. Both numbers are 1 + 2. Perform the addition. 1 + 1 = 2. Therefore, the final answer is 2.
Wow. It really did break it down.
It did, yeah.
Into those essential steps.
Right. No tangent complex math.
Yeah. No philosophical musings on numbers.
Just straight to the point.
Pure, straightforward reasoning.
And that's what's so amazing.
Yeah.
It shows that the LLM has learned to prioritize the most important information.
Even for something so simple.
Yeah, even for 1 + 1, it's like it understands this idea of thinking efficiently.
Yeah, and it's applying it everywhere.
Exactly.
This is incredible. It's like,
it's mind-blowing.
Yeah, we're witnessing a new kind of intelligence. And it's not just about knowing a lot of stuff.
Right.
But about knowing how to use that knowledge well.
Exactly. That's a great way to put it.
And that's what makes this research so exciting.
It really is.
It's not just about better AI.
It's about understanding intelligence itself.
Yeah, what does it even mean to think intelligently?
Right, and how can we design systems
Now,
think strategically, efficiently?
Maybe even creatively.
Exactly.
Wow, this deep dive has been a wild ride.
It has.
We've gone from the inner workings of LLMs to the limits of efficiency.
Yeah.
And even touched on some pretty deep philosophical questions.
It's been a pleasure exploring all this with you.
Likewise.
And for our listeners out there, we hope this has sparked your curiosity about the amazing potential of AI.
Absolutely.
Of the ongoing quest to understand intelligence itself.
Keep those brains buzzing, everyone.
Until next time.
See ya.